Hi and welcome back, and this is video 3 in our Introduction to Quantitative Chemistry, and we're still working on inquiry question 1, which is chemical reactions and stoichiometry. So today our lesson is looking at chemical equations. Now you would have perhaps been exposed to these in your Year 10 course, and we're certainly going to build on the knowledge that you do have. Certainly in the Year 10 you would have been exposed to writing word equations, and some of you may have been exposed, as I said before, to writing the chemical equations. So equations are used to describe what happens in our chemical reactions, and so we always start with writing down what happens in the form of a word equation. And this is something that you all have been exposed to, writing the word equations, which is writing down what our reactants are and what our products are in word form. So what does a chemical equation actually tell us, and why are we using them? Well, first of all, our chemical equations will tell us several things. They'll show us what species are acting in the reaction, so what are the reactants that are being reacted together, and what is being produced as the result of that chemical reaction. Now, our chemical equations are really good at ensuring that the law of conservation of mass is ensured through the balancing of those equations, but also they help us represent a fairly complex reaction in a more simple form. You might not think that they're so simple at the moment, but you'll do so many of these that you will end up thinking, what was ever so hard about them? So how do we do this? Well, the first thing, as I said before, we start with is our word equation. So our word equation is just simply in words telling us what two things are reacting and what product is being produced. So once we have our word equation, we need to work out the formula of all our substances. So using those skills that we have already practiced before about writing chemical formula. This is why it's really important that we become really confident in writing these chemical formulas down. And certainly if you're having trouble with that, you need to see me, because this is a concept that will carry across all the way through your chemistry studies. So then we're needing to look at the atoms and making sure that we have the same number of atoms of each element on each side of the equation. And so to do this, we have to put a coefficient in front of the formula that we have. So again, you will have heard of the word coefficient in your mathematics when you are looking at algebraic equations. So again, we put the coefficient in the front. That means then I have, if it's a 2 in front, for example, 2O2, that means I have 2 oxygen atoms. So if I don't have enough of those atoms on this side, we put the coefficient in front. We don't change that subscript there at all. Now we also need to include states in our reactions, and in the 7 to 10 we haven't probably been so pedantic about this, but this is where it is really important there as well. So we'll talk about that one in a minute. One important point is if there is no coefficient, again using say that oxygen example, if there's no coefficient in front of that species there, it implies that there is only one molecule of oxygen in that reaction. So we also have a reaction arrow, and that tells us the direction of the equation, or that the reaction is following, because you will see this again in equilibrium, that there are reversible reactions. Unlike mathematics where we use an equal sign, we are using an arrow to indicate meaning to form. Now, as I said before, we need to look at some of the states that we are going to use in a chemical reaction, and again you will become more and more familiar with these, but it's important to use the states in these reactions. So if we know it is a liquid that is being produced, we use the letter L in brackets. A gas represented by a G, solids with an S, and aqueous meaning dissolved in water. So liquids and aqueous might be your point of confusion. We use the symbol AQ. Now, in previous times, we used to write this like a subscript in small down the bottom, but now that we're scanning exam papers and so forth, sometimes it's really hard to determine the difference between an S and a G in a small letter, and also on how you write your letters, so it can make it a bit tricky. So we are now using them just as a normal size lowercase letter, just in a bracket. So these are really important to include because they actually will affect the energy change in a reaction. We'll talk about that a bit later. But it's also important to know the state of the product if I'm in a manufacturing industry and what is it going to produce. So what I'm going to get you to do is a little bit of a modeling activity. So this is in your booklet, and what we're going to do in our lesson is we're going to model some of these reactions, just so that you get an actual concrete physical way of seeing how the atoms are rearranged. So here I have got, and in your booklet I have got, that you're going to do some modeling using plasticine, rolling up some balls and making, say for example, a hydrogen molecule and a chlorine molecule. So if you don't have at home plasticine or Play-Doh, and you may not if you don't have younger brothers and sisters, improvise and use what you've got. You might cut out some colored bits of paper. You might do as maybe I'm about to indicate here, and we might actually just use some colored dots, but certainly physical modeling is much better. So say for example here we have a hydrogen atom, and we might change our color then, and we might make a chlorine atom, and you can see there in that reaction that hydrogen is H2 and chlorine is Cl2. That's why I have got two of each of those bonded together, and they add together to form HCl. So with our HCl we've got our H and we've got our Cl. So the law of conservation of mass states that the number of atoms of each species on the left-hand side should equal those on the right-hand side, which are our products. So how are we going to ensure this happens? I've got two hydrogens on the left-hand side. I only have one on the right-hand side, and the same with chlorine. I'm going to leave it there. I want you to have a go at those couple of reactions on the screen just there, and there'll be some more practice for you to come, and I'll see how you go at a later date. See you then.